Welcome to another Atom seminar. Today we have the pleasure to receive Professor Azahara Luna-Triguero. She obtained her degree in physics at the University of Cordoba. Then she was awarded her PhD degree in University Pablo de Olavide, which cum laude distinction. Her thesis dissertation was recognized for the Spanish Royal Society of Chemistry as one of the best theses of the academic course in 2018-2019. Now she is assistant professor in the section Energy Technology at Eindhoven University of Technology. She studies physical-chemical properties of porous crystalline materials for energy applications using classical molecular simulation techniques. Her main research interests are the adsorption-based capture and purification of valuable chemicals and adsorption-based thermochemical energy storage. Thank you again for accepting our invitation, Professor. Please feel free to start your presentation.
Well, thank you again for inviting me to give this talk. Well, as you already introduced, one of my research topics is thermochemical energy storage, specifically adsorption-based energy storage, and that's what my talk is going to be today. In particular, I'm going to focus on traditional and blended refrigerants in porous materials. And the reason why this topic is important is basically based on the energy transition. So everyone knows. Oh, it's not working. No. So everyone knows that if we want to make a transition between fossil fuels and green production of energy, that's the main goal. But the problem is that in general, in this case, there's maybe I can put the lesser pointer. Okay, so in this case is an example of solar production and consumption in a year. So the problem with renewable energies in general is that there is a mismatch between when the energy is produced and when it is consumed. So basically what this means is to make sure that we can use this energy when we actually need it. What we need to do is store it in some way. Well, there are three main storage or heat storage modes that we can talk about. One is sensible heat, latent heat, and the other is thermochemical. While sensible heat and latent heat are already commercial technologies that basically are based on storing the heat, so in changes of temperature by itself. Thermochemical energy storage, which is my main focus in here, it's still under development. It is based on transforming this heat into some other kind of energy, in particular, in our case, chemical potential. And the main idea to do that is because we have less losses, so it's more efficient, and also the amount of energy that we can store is higher than on the other counterparts. So basically, with that in mind, that's why this topic is really important. But of course, we are going to focus in a much lower or smaller systems in this case. So basically, my focus, as you already introduced, is crystalline materials. So we are going to use porous materials, either inorganic, organic, or hybrid materials, porous crystalline materials, so zeolites, MOFs, COFs, etc. We are going to need fluids, and in particular, in this specific talk, I'm going to focus on fluorinate molecules, and the reason is because traditional refrigerants in industry and in basically most of the applications that we still use have these fluorinate compounds on them. And the mechanism that we are going to use is thermochemical energy storage, as I said before, but specifically adsorption-based energy storage. meaning what we are going to focus on is to reproduce or to generate data of the amount of fluid that we can store in the inside porous, or the volume inside the material. And with that information, what we are going to do is just try to predict performance or efficiency for refrigeration systems or storage systems. So the main idea is that we are only going to focus from the molecular point of view, from the molecular perspective, computational perspective. We are only going to focus on this kind of absorption curves, so loading curves, in which we are changing pressure but maintaining temperature, in which we have no hysteresis. So this means we are going to focus specifically on reversible, perfectly reversible processes or mechanisms. And basically, the reason for that is because when increasing the pressure, we have this step increase and we fill the structure. What we want to do for the regeneration, which is an important part of this process, is to heat the system, and then it will go down to the loading, and we can completely regenerate, or hopefully go as close as full regeneration as possible. So that's the main focus of this talk. And before we jump directly on the fluorinate compounds and some specific examples of the structures and the behaviors, I want to introduce, so because of the systems that we want to use have many different applications, and the operational conditions are not actually fixed. So depending on the application, we have different temperatures, different pressures, but also different working windows in general. With what we need to know actually is the maximum amount of conditions as possible, so a screening of conditions in temperature, pressure, and loading, with the idea to obtain maximum information to provide the optimal conditions for specific applications, or the other way around, to find the better material fluid pair for a specific application. So with that said, we actually will like to focus on absorption isotherms. So we are going to be seeing a lot of these kind of graphs. And the idea is that, as I said, the output data is to have as many temperatures as possible, to have a wide range of operational conditions to explore. And the thing is, well, computers right now are very fast. We can do a lot of simulations. There are also a lot of experiments in literature, but there's also an increasing amount of materials every day that are being synthesized, and time is limited. So what we want to do is to do a screening of pairs, refrigeration pairs, as fast as possible and as accurate as possible. So what we want to do actually is to apply, or what we are working on actually is to perform an adapted thermodynamic model in a way that with only one single adsorption curve, in this case an adsorption isotherm, we are able to predict adsorption isotherms at a wide range of temperatures and pressure. How we do that? Well, we are using for processing the adsorption potential theory, and just by doing a transformation from the three variables, so three-dimensional space, to a two-dimensional space using the Dubinin-Polanyi theory, potential theory, we can indeed predict this wide amount of conditions. But of course, there's a catch, because otherwise this would have been done before, right? So the thing is that there are two variables on this two-dimensional equation space that need a bit of attention. So the two variables I'm talking about is one, the saturation pressure, and the other one, the density of the adsorbed phase. So in this case, the saturation, so what we want to do is actually know exactly the saturation pressure of the fluid at the conditions that we want to do. Those are variable with the temperature, and even if we know it for a range, it is not ensured that we can predict it for all the conditions that we want on the range of our applications. And the other problem is the density. And the first thought is like, okay, maybe we have experimental data for density, right? With different temperatures, and probably if a fluid doesn't have values or known values of this density, maybe we shouldn't use it, right? Because it probably not easy to use or is dangerous. But the problem is we are here talking about different things. So I'm going to focus first on the saturation pressure. For the model that we are going to use on the saturation pressure, we actually check different ones. And the thing is, under the conditions of under the operational conditions of refrigeration systems in general, and or storage systems, energy storage systems, we often are beyond supercritical conditions of the fluid on use. So it is true that in this area here, at normal conditions, in this case, I'm showing the example of carbon dioxide, we most of the models and most of the, except Dubini in this case, but most of the models are able to more or less reproduce the saturation pressure curve, temperature curve, for the fluids. But when we go beyond supercritical conditions, we actually have little knowledge of what is actually happening there. And therefore, what we did was to use several models to try to check and validate what is actually happening in them. And coming back to the density, the problem is that density of the fluid inside the pore does not behave equally as the density of the liquid in the bulk. Meaning the liquid density that we know, that we measure, it is not going to make it for the model. The reason for that is inside small pores, especially micropores and small mesopores. The Therefore, we need a model that predicts this new adsorption density, that takes account the compressibility factors inside the pore. Or in other words, we need this thermal expansion coefficient adjusted in a way or introduced in some way on our density values in order to be able to actually make this process predictable. And the thing that we use to do that is, again, the characteristic curve. So this two-dimensional curve to ensure basically it's a way, it's a mechanism, a tool to double check that we are actually using the correct assumptions. And we did that for several systems using all combinations of saturation pressure and density models and confinement. And what we found out was that the combination that worked best was using the critical isochord and the Hauer model in combination with the Dubini-Polanyi model to predict the characteristic curves. And this is validated basically because using different adsorption isotherms at different temperatures in the same system, by using the combination of the two adapted thermodynamic parameters plus the adsorption potential theory, all the values of all the different curves calculated at different temperatures are going to converge into this curve. And this is a good thing because the main property or the main predictive ability of this curve is based on thermal independence. So it's a good thing that we got this convergence. So what we did next was actually to try and predict some more absorption curves. So carbon dioxide in a specific structure was used to validate the model, but then we used different materials with carbon dioxide, but also with methane and nitrogen to actually try out. So what you're seeing here is from after taking one single absorption curve, usually at the lowest temperature, we predict their characteristic curve, and on doing the curve, we obtain these dashed lines, which are the predictions. For validating the model, what we did was to actually compute all temperatures that we were going to predict using classical molecular simulations to calculate these isotherms at different temperatures, and then we compare them. So basically what we see here is a comparison of what we obtained with the model, the predictions of the adaptive thermodynamic model, and the actual simulations that we perform. And we saw, so in this side you can see the linear the representation of the absorption isotherms, and in this side we can see the logarithmic representation, especially to make sure that the lower pressures, the really low pressures are well captured by the model. And we were very happy to see that we were able to make these predictions very accurately. But of course, carbon dioxide was going to, or we were expecting to really work out, because we basically use it as a tester for adapted thermodynamic properties, for the saturation pressure and for the density. So we thought, okay, let's test what happened when we change the structures and the fluids. But let's go also beyond that. And instead of only using values extracted from our simulations, let's try experimental values. So we went on a wide search of bibliography, and we tested our model on experimental values with different fluids or gases like argon, again, carbon dioxide, propane, ammonia, and methanol, and other fluids. And what we that had one of the requirements of it is that had more than one temperature, because otherwise we can validate anything. And what we found out was that we were actually able to predict a really wide range of fluids. And until the moment, we haven't found a system. We are still looking for a system that actually checks or provides with a limit. Especially, it is very remarkable the case of methanol in stamp 1. And the reason that we introduced this one was because we were kind of expecting it to fail and have an actual limit. The reason for that is because stamp 1 with methanol has a breathing effect, open gate opening effect. So the structure changes when in contact with methanol. So we were actually expecting the model to not be able to reproduce or capture these structural changes. But it did, so it was actually a very good thing. But also there is a particular reason why this worked in this MOF. And as a warning, if you are going to use this kind of models or this particular model, don't do it blindly on flexible structures, because this case is very particular and we know why it worked, but it is not guaranteed that it will for other systems. So once we have this model tested for several fluids, Um, what we wanted to do actually was to test it for refrigerants. But before going to that, we basically first needed experimental validation. So what the first thing that we did was to check some cases that I'm going to present are some case studies of the refrigerant 125 in MOFs. We choose 4 MOFs because they are very known, very widely synthesized. Everyone has some experimental values on it, so we needed them for validation. And so in this figure, you can see the values of the experiments, and in this side here, the size of the simulation colors for the same structure. And even at the first glance, you will see more or less a very good agreement, except for UVO 66, but I am going to come back to that one later on. This was not straightforward. So one of the things that I wanted to remark in this presentation is to not blindly use methods without proper validation and testing, um, and just assuming that it's going to be transferable. Let's be correct, and let's be accurate, and try to validate always as soon as it is possible. And we have a possibility for experimental validation. Let's focus on this experimental validation and then try to predict other behaviors. Otherwise, we are setting bad habits for future research. So the first thing that we did was to try to indeed do this experimental validation, but let's say it's not trivial. So I'm going to go case by case in this for each MOF. So MIL 101 actually had no problem at all. We ran the simulation, and it was perfect. It was in very good agreement with the experiment. So we pass to the next one. The next one is Copper BTC, or CUST1, a very well-known structure. And the problem with this structure is the next. So when we ran the first simulation, we found this gray line when the experiment was actually constantly below. The reason for that in this case was known for us because we had worked before with this structure, but it is not trivial. And if you don't know the structure, it is easy to be overlooked. And the reason is that this kind of molecule won't fit on the small pocket size. So the size of the window, or the size of the cage, sorry, the size of this adsorption site, it is big enough to have the molecule inside. The problem is the diffusion channel that connects with the big cages won't allow the molecules to get inside. So for the case of this particular molecule, this cage is inaccessible, and we had to introduce artificial blocks on these windows. Once we did that, we actually obtained the blue line, which actually fits perfectly with, or almost perfectly, with the experimental values. Explaining again that we cannot take it for granted that our models will work. Even for the first structure work perfectly without any changes. The second one had specific properties of the structure that may change this a bit. For the second structure, we actually have CIF8, and in this case, while CIF8 is a flexible structure, we have the ambient pressure phase and the high pressure phase, and then we check both phases using an approximation in which the structure is actually rigid. So we have the two phases as separate simulations, but we have both. And in this case, what we can see is that even if we are not actually at that much high pressures, the behavior of the structure or the behavior of the adsorbent in this structure make it goes through this high pressure, the so-called high pressure structure, and only after ambient pressure we actually see a change for the high pressure one, for the ambient pressure one, which makes sense because it's actually the change happens at 100 kilopascals. So on the last case, it's actually a fail case, and with that I mean it is very important that to acknowledge that bad results are still results. And in this case, what we use is UEO66, a very well-known structure. We have the crystalline phase that failed strepitously to reproduce the experimental data. And then, well, it is well known that this structure is very stable even with defects. So we try to add some defects, eliminating parts of the ligands, of the organic ligands of the structure, some atoms, then actually minimizing the structure to to see if it collapsed, and once not, actually redo the simulations. And as you can see, even with some of the defects added, we could increase the loading, but the lower part of the curve, the beginning of the adsorption isotherm actually indicates that in the experimental case, probably they have or larger defects, making it a mesoporous structure, so the entrance is shifted in pressures. And also the other possibility at high pressures or beyond this 100 kilopascals is that there is experiencing some external surface adsorption and no longer inside the pores, which we cannot account with this specific kind of simulations. So anyway, this didn't work out. Then we proceed with the study with only 3 structures for the refrigerants, having mil 101, copper BTC, and C8, which reproduce pretty well the experimental values. So once we have this, the other thing, as I said before, there's plenty of structures, plenty of different fluids. We want to minimize the computational time as much as possible. That's one of the reasons we work on the adapted thermodynamic model, but we also want to minimize the computational time as much as possible as well. Without losing accuracy. So what we did was to try out some we try some model variations, so model approximations. For the first simulations, the ones that I showed until now, we were using flexible molecules and a charge system, meaning that the MOF, the structure, had pointed charges as well as the molecule, and the molecule has flexibility, meaning that it accounted for movements, vibrational movements, angled movements, and torsions of the molecule. So the first approximation that we did was to maintain the charges of the system intact, but block the flexibility of the molecule, making it rigid. So the molecule could still move, could still change, but could not get distorted or get in different configurations. The second approximation that we tried was to not change the flexibility of the molecule, so maintain the flexible charged molecule, but take out the charges of the structure. So the structure doesn't interact with electrostatic potential anymore with the molecules, but the molecules between them do. And the last trial that we did was to maintain the flexibility of the molecule, but take out both charges, the molecular charges and the system charges. And this was basically to try to accelerate the results of the absorption calculations with the Monte Carlo simulations. So quite surprisingly, or not, or because this is maybe like a unicorn a MOF SIF that always or almost always seems to work out. CFATE seem to don't it seemed not to be very important, the model variations that we use for the reproduction. There was a slight decay in loading, so a small underestimation in the entire curve when we use the flexible molecule, but no charges in the system. But apart from that, it seemed like we can basically neglect anything. That is not the case for the other structures. So as we can see here, for either copper BTC, but also MIL 101, when the flexibility of the molecule doesn't seem very important, so the charges of the system are really part of the absorption mechanism. So the uncharged system couldn't reproduce the shape or the loading in any of the cases, but very special and very noticeable in the case of MIL 101, and this is due to the amount of molecules that can fit inside this mesopore structure. For the uncharged MOF, there was also a lack of clarity, especially in the middle of the absorption on the transition. The lower at low loading and saturation seem to be reproducible, but the shape of the isotherm again was not able to be reproduced with this model. But in the case of the rigid molecule, so we are not using we are still using charges for the structure and point charges for the molecule, but we neglect that we delete the molecular configurations within the same molecule. It seemed not to affect to this to the absorption properties. Therefore, it is a good idea to try the limits and to check whether we can do some of these modifications. Again, this is not something that we should do without testing, because in this case, the flexibility of the molecule is not important because it's small enough. But for longer molecules, this will probably not be the case. So with that warning in mind, once we have this validation, this absorption property well developed, we are able to predict, so we can move to different temperatures and conditions. What we are actually want to do is to proceed to insert some of these operational conditions that the systems under study are going to actually use. So in this case, what we did is to fix in a very strict way the absorption and desorption conditions and calculate the working capacity. So how much loading, how much difference of loading can we charge and discharge, so recover after a cycle of absorption and desorption at very specific conditions. We call this a TSA process, so thermal swing absorption process, but it's actually a very rough approximation of it. In which what we wanted to do is to test whether we were able, with this approximation, to capture the most essential parameters and properties for the prediction of the systems. So with this parameter, with having this the working capacity, we choose for example this pressure. We say, okay, we are going to work at this desorption pressure. So for MIL 101, we actually have 6 mole per kilogram of this refrigerant. And we have on the other side of the slide the enthalpy of adsorption or heat of adsorption. And the reason for it is why this is important is because this interaction basically give us information about the storage density of the system. So knowing the amount of the conditions, the amount of the working capacity, and what loading do we have at these selected conditions of temperature for adsorption and desorption, what we actually choose is this regime. And the integration of this area, it's actually by definition the storage density of the system. So it is pretty important that for our systems we are able to reproduce the adsorption capacity, but also the energetical part of it, because basically that's what gives us the information that we need for the processes. So the same that we did for the TSA, we did for rough estimations of processes for PSA and PTSA, so combination of the pressure swing and pressure temperature swing, apart from the temperature swing adsorption. We fix this very rough and very specific adsorption and desorption temperatures. We choose in a very random, just for validation, not for validation, but for testing purposes, 200 kilopascals as adsorption pressure. And what we did was to calculate the storage density as a function of the variation of these models. And even it is a very rough estimation, and we are actually talking about very low amounts, so only 30 degrees of temperature lift for these systems. The values that we obtain for the storage density that we could compare with literature, with experimental literature, were very good. So even if it is a rough approximation, it will help to build a first approximation and a first design for the processes. So this is actually very nice for pure refrigerants, right? For pure fluids. But I actually wanted to introduce blended refrigerants. The main reason for blended refrigerants is that they usually are just basically a combination of different ones, and they were meant to be as substitutes with lower global warming potential for refrigerants that were used on other systems at the time. So one specific example is air conditioning. At house, the house use refrigerants is usually air 134A, but before that one it was air 22 or air 23, and those are not only high global warming potential refrigerants, but some of the old used refrigerants has also ozone depletion power. So we really need alternatives to change the existing refrigerants into more sustainable ones, but we don't want we want to change the systems the less as possible, because the infrastructure is already there. So we don't want to change everything from scratch. We want to reuse as much as possible the systems and the conditions that they are able to use, and the blended refrigerants are a good alternative way. So what we want to do with blended refrigerants is basically similar with a similar approach that we use for the pure ones. We choose the adsorption of the ternary mixture, so the ternary mixture, and we calculate the adsorption isotherm. In this case is MOF 47, if I remember correctly, but it is not important for the case study. And what we want to do is, or the power that we have with this reproduction, is that we are not only able to produce this curve, which is like the gravimetric capacity curve that one will obtain in an experiment, balance, change balance one. But we are able to know the specific contribution of each one of the refrigerants in the mixture to the total loading. And this is not important by itself, but if, for example, we have a system and we choose to work around 10 bar, in this case, again, the most important thing is not only reproducing the adsorption isotherm, but the enthalpy of adsorption, because it's what provides the value of the storage density. The combination of both is what provides the viable calculation of the storage density. We have this contribution here. So we are able to say, okay, our refrigerant, the contribution of our refrigerant 125 to the total storage density is that one. And this provides valuable information that I will explain later on. But the idea is that we are not only able to know the storage density and the heat, the enthalpy of adsorption or the total loading, but we know which one of the refrigerants, which one of the fluid of the mixture are responsible for it. And understanding the mechanism and understanding the responsible parties on this is a really important, it's a critical point to actually design new refrigerants and to design new systems. So the thing is, we want to compare which materials are better. And of course, if you think of, okay, if one of the main parties, one of the main parameters is the loading, right? Then we just use big structures, we fill them, and then that's it. As much space we have, we will have a lot more refrigerant, then a lot more storage density. And this will be true, but we are always restricted to conditions, meaning operational conditions are very important. And this is just an example. So we have the two mixture refrigerants, the 407F and 410A, so the ternary and the binary refrigerants. And we have two structures. As a micro porous structure, we have copper BTC, and as a mesoporous structure, we have MOF 177. So in this case, we will say, well, clearly, MOF 177 has a lot more storage capacity. Therefore, we will use that one for storage. The problem is that this is only true if we are able to reach the conditions that lead to this high capacity. In usual systems, we are going to have these preconditions, these conditions preset, and we cannot actually change them. So if we actually focus at ambient conditions, what we have is that for copper BTC, we will have a loading slightly bigger than 5, while for the MOF 77 at the exact same conditions and the same refrigerant, we'll have way lower loading, meaning that even if MOF 177 has higher capacity, we are not using it. And not only that, if we see the shape of the heat of adsorption, so the enthalpy of adsorption in here, we can see that copper BTC, just because of the size, will have higher interaction with the molecules, meaning that if we blindly choose the bigger MOF, we are not only restricting ourselves of some loading, but even if it was the same, we are sacrificing the interaction which will provide the storage density. So for these same conditions, the storage density of copper BTC is actually pretty high at these conditions, while for MOF 177, which will you expect at the beginning to be the best one, it's actually 1/3 of it. So again, do not use do not choose blindly the systems. It is very important to have in mind from the beginning of the design, from the beginning of the design, from the beginning of the simulations, what are the operational conditions in which our systems are restricted, to actually choose the better options, the more efficient ones. So what else can we actually do with these refrigerants? Well, the main idea, so this idea is pretty good, but can we actually apply the same model that we use for the pure components? So this thermodynamic adapted model, can we use it for reproducing or for predicting a huge variety of these conditions? So we don't have to do this every time that we need to check the conditions, the adsorption and desorption conditions of a pair. So can we have this three-dimensional prediction, this adsorption isosurface as a function of loading, temperature, and pressure for the blended refrigerants, so we can actually do a faster screening. So the first test that we did on that are basically done like that. So what we tested and what we can do as the moment is by using the pure components at one temperature, in this case 303 Kelvin, we can actually predict the adsorption capacity of the blended refrigerant at a different temperature. And the procedure is quite simple in general. So we do the calculations, or we take from experiment the pure components at one temperature. Then we apply the thermodynamic model, the adapted thermodynamic model, isocritical, critical isocore, Howard density model, together with the Vini-Polanyi. We calculate the characteristic curve and predict the pure components at different temperature. And from these different temperatures, we can actually, in this case, we use IAS because it's the most extended one. We can actually predict pretty accurately this the absorption curve for the blended one. So the curve is the prediction going from the pure thermodynamic model and IAST, and the symbols are the molecular simulations done directly at these conditions for the ternary mixture. Of course, there's a but, and this is exactly in this lower regime. We slightly underestimate in this case, or the model underestimates slightly the capacity over the molecular simulation data. And the reason for that, it is probably because we are using IAST in this case. And even if generally at low loading, it will be valid to assume this non-interaction between the molecules that are being absorbed. In this case, there are two refrigerants, the 125 and the 134A, that probably are competing for the same absorption sites. And this makes the prediction shake a bit when we are assuming this non-interaction between the fluids. So our next step, of course, is to try to improve this part using different models, so probably Rust, taking into account the interactions. So once we know that we are able to roughly predict the the absorption of the blended refrigerants, the next step will be use this information and specifically the contributions of each one of the components of the mixture to try to generate new refrigerants. And with that, what I mean is basically we are going to use for a specific case how in the center, how the molar fraction inside the structure changes along with the conditions, so we can monitor that. Um, um, in the dashed lines, we have actually the conditions of the fluid in the bulk. So the actual condition of the refrigerant that you buy has this composition, and then we can see how it changes along the conditions, the working conditions. And this is a pretty interesting thing to do, because what we see, for example, in the ternary mixture is this, again, if we are working here at ambient conditions, that, for example, the contribution of R32 in the mixture is pretty low, is below, in this case, 0.1 of the total capacity of the structure, which in this case is around 2 or 2.5. And what this means is that the total contribution of this refrigerant to our storage density is actually only this chunk of here. So if we go to this condition and we know that we have around 10 mole per kilogram in the green one, we are actually, yes, we are taking a chunk of it, but the contribution is so low that maybe it wouldn't be a bad idea to use a refrigerant that doesn't have content of R32 for this specific mode. So the idea is, one, to know which material is going to behave better or use better the contribution of a specific refrigerant. And the other thing is that why don't just take out the R32 and use just a mixture of the other two refrigerants? Will it improve? Will it stay the same? How much will it affect? And this will provide information on creating new refrigerants or new blended refrigerants in this case, which is, I think, personally is very promising. So to end up, I want to I want to go to the conclusions and highlights. So the first thing I want to remind is about the thermodynamic adapted model that we provided, in which with an input of one single absorption curve at one temperature, we are able, using the combination of the critical isochore, the Hauer density model, and the Duvini-Polanyi absorption theory, predict several absorption conditions, and these help us to build the three-dimensional absorption isosurface, which basically provides information of a wide range of operational conditions that we can choose. And on the second hand, we can use all this information for thermochemical energy storage using refrigerants, using those three-dimensional, this absorption isosurface, the three-dimensional representation of the absorption. We have a better chance to produce a process design that will lead to optimal values. And this basically looks like that. So if we perform a process design, an estimated process design in three dimensions, we can then use performance indicators. In this case, a specific cooling effect for a refrigeration system, in which we again have a wide range of operational conditions on the system that will provide a good performance or a good efficiency for the systems. So our main goal now is to actually try to do the same with blended refrigerants, with the hope that that if we are good enough reproducing this and have enough data to optimize the processes, we can actually go for more environmental friendly refrigeration systems for or energy storage systems in general. So thank you very much for your attention, and I'm happy to take any questions that that the audience may have.